Hi there. The research topic in my group is site-specific catalytic catalysis. Many of you may have heard of the concept of catalytic catalysis, but what you may not know is the biggest feature of the catalytic catalysis is actually the structural heterogeneity. Because many of the catalytic catalysts, they are composed of defective surface with all kinds of surface species, and that will give you very complex surface structures. For example, over here, this is showing a TEM image of aluminum-supported tungsten oxide species. You notice that all kinds of surface species. You have some single atoms, some dimers, some trimers, and also some big clusters. So this is a very common image for all kinds of catalytic catalysts. So with this complex surface structure, how can you understand the structure property relationship of the catalyst? And how can you design a better catalyst to promote the performance of the catalyst? So that needs a lot of research, and that is the research topic in my group. Because of the structural heterogeneity of the catalytic catalyst, understanding the structure property relationship of the catalytic catalyst is very difficult. So in our group, we adopted two different approaches to address this issue. The first approach is the model catalyst synthesis. We use a well-defined synthesis approach to control the surface structure of the catalytic catalyst to make it more uniform so that we can understand the structure property relationship better. The other approach is using the site-specific spectroscopy. So for example, if you have a complex surface structure with all different types of species, but if you have a spectroscopy technique that can identify each site and can monitor the chemical reaction on each site, basically can know the structural property relationship of the catalyst catalyst. And after that, you can design a catalyst with a more uniform active site to increase the performance of the catalyst. I'd like to show you two research examples to demonstrate the concept of our research. So in the first example, we use infrared spectroscopy with the carbon monoxide molecule as a probe molecule to distinguish the surface structure of this supporting plasma catalyst. So the supporting plasma catalyst is very useful for the carbon monoxide removal in several reactions. But understanding the active site is very difficult, has been highly debated. So using the infrared spectroscopy, we are able to observe two different bands over here. So one band is related to the carbon monoxide on the platinum single atoms, while the other band is the carbon monoxide absorbed on the platinum nanoparticles. After the absorption, you can put in oxygen to oxidize the carbon monoxide. We can clearly see that only the carbon monoxide absorbed onto the platinum nanoparticles can be oxidized, while the other band is very stable. That clearly tells us that only the platinum nanoparticles are active for this reaction. Another example I want to share with you is something we developed recently. This is about the biometallic nanoparticle synthesis. We know that the biometallic catalysts are very useful for the chemical industry, but synthesizing the biometallic catalyst is fairly challenging, because how can you control the two metal species on the surface? They can stay together all the time to generate the synergy. What we did over here is that we first modified the surface and absorb the metal cation species on the surface, and then you introduce the metal anions. The metal anions are gonna target on the metal cation. They're gonna form the double complex salt on the surface. So this is what we call the surface inorganic metallic chemistry. So after you form the double complex salt on the surface, then you reduce it and remove all the ligand. The metal species can stay together and form some nanoparticles. So this is a very nice way how you can control the two different metal species. They're gonna stay together all the time and give you the maximum synergy during catalysis. I hope through those examples you can have a better understanding about the research principle we have in our group. And if you have further questions, please feel free to contact me. And this is my email address. And you're welcome to apply to LSU.